Okay, so we will continue today with these lectures of the next chapter. And so this is actually real valued multiple variable functions. So let me just okay, so let's just start from the beginning. So how do we define a real valued multiple variable function or several variable function? Well, I mean, this is a function that goes from Rn to R, and let me just make this a little bit bigger. Okay, so from Rr to R, so the value of that, the value of the function, is still a real number. That's why we call it a real valued. Okay, and here we have basically several variables that come from Rn. So let's just make this a little bit more precise. So the domain, so let's just look first for a function with two variables. So from R squared to R. So the domain of it is some subset of R squared, let's just say D for the domain. So this is a rule that going from any point here, xy, to some value. So a visual representation of this is, let's say this is the region D, yes? And so any point here, and this is the R, the right plane, this is the R. So any point here, any point will go to some value of R, okay? So this is one way to think about it. Of course, the D is called the domain, and the set of values is basically the range, as usually we call this for functions, okay? So let's just see a couple of examples so you can have some idea of what is happening. So we can actually talk about the domain and the graph of these functions and so on. So what is, for example, the domain of this function? F of xy is equal to x squared plus y squared. By the way, we normally write a third variable here, so we say z is equal to x squared plus y squared. Well, the domain here is basically anything you want for x and y, because there's no problems here. We can compute for any point xy, any ordered pair xy, we can compute the value of the function. So the domain will be all of the r squared. The range on the other side is only these values for z are only positive, because the right hand side can never be negative here. So they are only these non-negative numbers, so positive or 0 or positive. So we call this, well, that is really the range. So if you actually have some kind of a graphical representation of this, here is the domain. I mean, somewhere here in the xy plane is the domain, all of it. And then for each one of them we have a z value. So that's how actually this looks like, the value of this function. Maybe in one of these lectures I even show you some animations of this in Maple, how to construct this and how to build these graphs. Here is another one, another function, f of xy is xy. Again, here the domain is r squared, and the range is, you can show here that it's all of r. So this will be something that we will see again. This is a surface basically that gives us an illustration of what we call it a saddle point, okay? So we'll see this is kind of a special surface. All right, what about another one? So what about the domain of this other function? See, square root of 9 minus x squared minus y squared. Well, in this case, I mean, the function makes sense only when that value inside the square root is not negative. And you can play with that, but that basically means that this thing is not negative, so x squared plus y squared is less or equal to 9, which means that the domain is this disk here, including the boundary of the disk, okay? So this is basically just to give you some ideas that, yeah, we can talk about the domain. The domain will be some region of r squared, and we can talk about the range, which is basically some region of r. okay, usually in the z-axis. Okay, so what about these graphs? Well, I mean, so let's just continue a little bit. As we did for functions with one variable in pre-calculus, I mean, that's what we do here. So this brown region here, I mean, down in the xy plane, that's the region D. For each one of them, we have a z value, or the value of the function there. So this S here, up here, this blue region S, that is really the graph of this function. And the brown one here in the xy plane, that is the domain of this function, okay? So yeah, one can play with this, and there are a lot of examples in the book that you should look at. For example, construct the graph of this function. Well, I mean, so you have z is equal to this, right? Well, we know this is from the previous chapter, this is a plane, right? So in this case, all you have to do is pick 3 points on this plane, and you can pick 3 points easily here. You give values to x and y and find z. And so in this case, is this plane that goes through these 3 points as shown in the picture, and of course continues, right? And the graph here of this function that we did, we saw here in example 4.3, right? This function here is what? Well, now we said that this is the z, and z is given by, so here, right? Z is here, and if I square both sides, z squared is that. But again, I will only take only the z non-negative values because they come from a square root. And so what is it? Well, I mean, this thing I know what it is. If you take x squared and y squared on the other side, this is this equation here, which is the sphere with radius 3 and center at the origin. And so what happens is that, you know, I'm taking only the non-negative values for z, so I have this semi-sphere here, or hemisphere here. The northern hemisphere, right? The upper one. All right, so level curves, or contours, we call them. Well, these level curves are very interesting, and they show up in a lot of applications and so. And let's just define and see what these level curves are. Suppose the blue one here is some surface that we have the graph of a function with 2 variables, right? And if I want to somehow represent this as on a map or on a piece of paper, so I don't want to build some kind of a 3D graph, but what I do is I just cut this surface with these horizontal planes. And when you cut it, they have these lines. You see these horizontal lines? These, I call them the level surfaces. But it makes more sense to actually represent them down here. So this blue cuts or lines up here become, now look at what they become. So they become, you know, these pink lines down here. And if you see, each one of them has a small number there, which is basically, let me make this a one page. So you see, I mean, each one of them has a small number, which is basically saying that this level here is this value of the function at this one is 20, for example, and this one is 25, and so on, because each of these, all of these points on the surface that belong to this pink circle, the outside, for example, have the same height, because the cutting plane was horizontal. And so normally you might have seen in these topographical maps, you might have seen things like this when we want to represent a mountain, for example. We show basically things like that. Anyway, so if I were to actually graph, let's say, this following function that we saw before. So we have this, that is equal to this one, and I want to graph this. What do we have? We have that z is equal to c. So basically this thing is 9 minus c squared. So what do we have? We have the circles, right? We have the circles when we cut this with radius 9 minus c squared. And so representing them on the xy plane, that's how they look. Okay? They look maybe like ellipses, but they are actually circles, right? Anyway, Now I think this picture here probably belongs to the next one. Yes. So this is the picture actually belongs to this one. So these are now another function. And I want to construct the level curves for that. So I will let it be equal to c. Now notice that for this one, the coefficient in front of x squared and y squared, they're both positive, but they're not equal. So we get an ellipse, not a circle. And you can write it this way if you want. But anyway, and that's why these level curves correspond to this example. They are these ellipses, okay? Anyway, what about in real life? I mean, you can get oops, sorry about that. I mean, you can get, for example, many applications and many objects in real life that make use of these level curves. For example, I mean, in hills sometimes we build this level curves this way to plant trees and things like that. So this is an actual shot of a satellite image of one of these things, okay? So there are many ways that you will see this in nature. All right, can we have functions with more than 2 variables? Of course. Can have functions with 3 or more variables. So a function with 3 variables now will be, the domain will be some solid, some region in R3, okay? And the domain will be basically that D and the range, whatever it might be. And of course, this has to be a function, right? I mean, so it still has to satisfy the definition of being a function. Okay, so for example, let's just find the domain of this function. Well, here there's no restriction for any x, y, and z that you put there. You can compute that value. So this is all R3, all of R3. But the range is, well, this is an exponential function, so the range is always, the values of this are always positive. Okay, so you can actually do all of these things. So I have a couple of easy examples here, and so you can look at the next example. Here now we don't talk about level curves, but we talk about level surfaces. Why? Because now we have the solid D, and when we actually say, okay, let this function, for example, I mean, let this be equal to, I'm sorry, this one be equal to a constant k, here it is, then we get something in the domain, right? But we cannot see actually what happens in the graph, because in that case we will need, well, 4 dimensions, which we cannot really visualize. I do have, I believe, one example of this where you can get, where you can get an idea one more time than what happened to this. Yeah, here. What happens to this now? So let's just see. Yeah, this is an example. Man, what is happening? This is an example. So, for example, so let's say this is the function of 3 variables, and if I want to find this or see how they look, these level surfaces on the domain, well, I'll have to let this function be equal to a k, and if that happens to a constant k or c or whatever, so what is that? You get these peels of this sphere, right? So every peel there is kind of a level surface. Okay, so there are a few examples there at the end where you can find the domain and the range of a few functions there. So I will stop here and we'll continue in a second for the second part of this lecture. Thank you.